We're now going to learn about a special kind of permutation called a cycle. So the definition is quite long, but actually you'll see in the examples it's quite a simple idea. You start off with picking a number m, a positive number, and then m distinct positive integers. So we'll call those a0, a1, a2, up to am minus 1. Then the cycle, which we write like this, is the permutation that sends a0 to a1, and a1 to a2, and a2 to a3, and so on, until we reach the end of the cycle when am minus 1 gets sent back to a0. So that's this clause in the definition here. And then finally, if there are any numbers which don't belong to the cycle, then those are sent to themselves by this permutation. So let's see a couple of examples of this just to see what's happening here. Let's say we talk about the 3 cycle 1, 2, 4 as an element of S4. So this is the permutation which sends 1 to 2 and 2 to 4 and then 4 back to 1 again. So if we were to write out the 2-row notation for this cycle, it's an element of S4, so it's a permutation on the set 1, 2, 3, 4, and as we've seen, it sends 1 to 2, 2 to 4, and 4 back to 1 again, and then 3, a number which is not part of the cycle, will simply be sent to itself. So this 3 cycle 1, 2, 4 is the permutation whose 2-row notation looks like that. Let's see another example. So I'm going to take the permutation 2, 5, 7, 1, which we're going to look at as a permutation in S7. That is another cycle, and in this cycle 2 goes to 5, 5 goes to 7, 7 goes to 1, and 1, when you get to the end, goes back to 2 again. So if we want the 2-row notation for this, I should have 1 to up to 7 on the top, and 2 went to 5, 5 went to 7, 7 went to 1, and 1 went back to the start of the cycle to 2. All the other numbers will be sent to themselves. So 3 doesn't belong to the cycle, so this permutation sends 3 to 3, and 4 to 4, and 6 to 6. Okay, so if you want to see why these things are called a cycle, let's just draw a diagram here to help us understand the permutation. You've got the number 1, which goes to 2, the number 2 goes to 4, and the number 4 goes back to 1 again. So you can see the numbers go round in a circle like this, and hence the word cycle. And similarly here for the cycle which we wrote as 2, 5, 7, 1, 2 will go to 5, will go to 7, will go to 1, round in a circle like this. Alright, so the definition I've got at the bottom of the slide here says that a permutation which we wrote like this is called an M cycle. So M is the length of the cycle, the number of things which are in the cycle. So this here would be a 3 cycle, and this thing here will be a 4 cycle, because there are 4 numbers in the cycle. Okay, so that's our definition of cycles. Now, an important thing to notice about the notation that we're using for cycles is that there are many different ways to write the same cycle. So if we think about this 2 cycle here, 1, 2, and perhaps we think of this as an element of S2, and we wonder which cycle is it, which permutation is it? Well, it sends 1 to 2, and then 2 is at the end of the cycle, so it goes back to 1. But equally, if you wrote it like this, 2, 1, if you look at that cycle there, again, that's the permutation which sends 2 to 1, and then 1 is at the end of the cycle, so it goes back to the start. So we have the same permutation as before. Both of those permutations sends 1 to 2 and 2 to 1. So these things are equal. Similarly, if we take a 3 cycle like the one here, we can write it in 3 different ways, because you could choose to start this cycle in any of 3 different places. So this is the permutation which sends 1 to 2, 2 to 3, and 3 back to 1 again. So you could choose to begin writing your cycle at any one of those 3 places. And if you start it with a 1, then 1 goes to 2, 2 goes to 3, and 3 goes back to 1 again. So you get the first piece of the first cycle that I wrote there. If you choose to start it at 2, well, 2 goes to 3, 3 goes to 1, now you're at the end of the cycle, and 1 goes back to 2. And you can also write it starting with 3. And similarly, if you've got a 4 cycle like this one, you could write that cycle in 4 different ways, because you could choose any of the 4 numbers in the cycle to be the number which appears at the start. So the cycle notation has this property that there are several different ways to write a given cycle using that notation. In fact, there are m different ways to write an m cycle. Let's record this fact. So every m cycle can be written in m different ways using this cycle notation. And that's because you could simply choose to start your cycle notation at any point during the cycle. Okay, disjoint cycles. There's a really simple definition, but which will become important later, which is the definition of disjoint cycles. So 2 cycles are disjoint if they don't have any numbers in common. So for example, if we had 1, 2, 3 and 5, 7, there are no numbers which belong to both of those cycles. So these are disjoint. On the other hand, if we took 1, 2, 3 and 2, 7, well, the number 2 belongs to both of those cycles. So these are not disjoint. And one of the reasons that this concept of disjoint cycles is important is that you saw in general in the previous video that permutations don't commute with each other. So in general, if you've got 2 permutations s and t, then s composed with t might be different to t composed with s. That's not true for disjoint cycles. So if you have any 2 disjoint cycles, then they do commute. So let's record this. You're going to be proving it on one of your courseworks, so I'm not going to give a proof of this. So let's just record it here. So fact, and you'll see this on coursework 2. If S and T are disjoint cycles, then they do commute. S composed with T is equal to T composed with S. Right, last thing that I'd like to say about cycles is about the inverse of a cycle. So let's take, for example, a cycle 1, 2, 4, like this. So this cycle, let's call this S, sends S of 1 is 2, S of 2 is 4, and S of 4 at the end of the cycle goes back to the start, so S of 4 is 1 again. So what should the inverse of S look like? Well, the inverse of S should be a permutation which sends, well, since S sent 1 to 2, S inverse should send 2 to 1. And since S sends 2 to 4, S inverse should send 4 to 2. And S sends 4 to 1, so S inverse should send 1 back to 4. And the number 3, for example, S sends 3 to itself, so S inverse should send 3 to itself. So let's record this one. S of 3 is also equal to 3. Okay, so what is this description I've given you of the inverse permutation? Well, if you just wrote the cycle backwards, that's exactly what the inverse does. S sends 1 to 2. This cycle written in the opposite order sends 2 to 1. S sends 2 to 4. S inverse here sends 4 to 2. S sends 4 to 1, and S inverse, as written here, sends 1 back to 4. So you can get the inverse of a cycle by just writing the elements of the cycle in the opposite of order. So here is the general result for the inverse of an M cycle, A0, A1, A2, up to AM-1. Its inverse, which as usual we use the same notation as we use for inverses of functions because our permutations really are functions. This inverse is just another M cycle with the numbers written backwards. So let's do one final example of the inverse of a cycle. If you took, for example, 1, 2, 3, then its inverse will be equal to the cycle 3, 2, 1. That's just this cycle written in the opposite order. And of course you can write this in other ways if you like. We know that you can write a 3 cycle in any of 3 different ways. So you could start this at 2 if you like, and it will be 2, 1, 3, or you could start it at 1 if you wanted, when it will be 1, 3, 2. But that is the inverse of 1, 2, 3.